So I want to talk to you a little bit about the emergence of abiotic organic chemistry on young planets, and predominantly focus on Titan. This was spurred years ago when Cassini was getting ready to take off, and a bunch of us at Arizona decided we would start thinking about the chemistry of this organic-rich object. So, table of contents. Last night I threw away all my early Earth slides, since that was dealt with quite well this morning by people much more educated in it than I am. I'll talk to you about Saturn's moon Titan and its use in the laboratory as an analogy to early Earth, to try and understand how far and what pathways organic chemistry proceeds upon in the absence of life forces, and in particular how we can use laboratory techniques to support mission science. And then about 3 in the morning I woke up after our breakout session where I had tried to convince people that homochirality is an emergent phenomenon, and so I threw a few slides in to talk a little bit more about homochirality. And I'm still not sure it is, but we can talk about it anyway. Okay. Nature of abiotic organic chemistry. Organic chemistry is ubiquitous across the universe. Our evidence of it, unfortunately, tends to be either extremely simple molecules like methane or carbonaceous refractories, which I consider as chemical history of complex organic chemistry. But the palette of organic chemistry, Jim had a great slide that just shows you for one mass how rich the organic chemistry can be. I'll show you for 1,000 masses how rich the organic chemistry can be in modeling organic aerosols of Titan, and hopefully convince you that in some regards atmospheres are necessary active mixing devices. Not to say that hydrothermal vents and ocean systems, as we heard this morning, can't be the same, but atmospheres are great in delivering small organics up to light sources, energetic photo sources, and then allowing them to settle back down to the surface where they can do more conventional chemistry as larger molecules. And so the atmosphere eventually provides, especially on Titan, a feedstock of a large menu of organic compounds on the surface that, given appropriate conditions, such as an ocean on other objects than Titan, that allow solubility of these objects and eventually solution phase chemistry that can occur under more normal, lower energy conditions. So what constitutes a rich life-related organic chemistry? Carbon, hydrogen, nitrogen, and oxygen. I saw this spelled as chomp yesterday, but I've left out the phosphorus and the sulfur. It's complicated enough just focusing on CH and N and O, and really on Titan, we'll just focus on CH and N. Eventually, one presumes these will need to be solubilized before they can start undergoing textbook-type conventional chemistry. And even some of the refractories can break down under such conditions and yield small molecules or moderate molecules to undergo that. We also need an energy source. And with regard to atmospheres, that energy source can deliver small molecules up into radiation fields deep in the vacuum ultraviolet, where we can store large amounts of electronic potential in the young products. hydrolytic or oxidative potential that can then eventually be used, hopefully, on a system for which life is evolving. And also, I think it's very important that that this atmosphere that is cycling the organics in this chemical synthesizer is reducing in nature. That's critical. Otherwise, in the presence of oxygen, the carbon chemistry is going to be more combustive and break down. You're not going to get as diverse a sampling of rich organics as you do in reducing atmospheres, nitrogen-containing reducing atmospheres. Okay, my one slide on early Earth. One has to produce an atmosphere, one has to deliver carbon, hydrogen, nitrogen, oxygen, and some other compounds to this atmosphere in order to get this organic synthesizer going. On Earth, I think this moon creating event was critical in doing that. It brought in exogenous carbon, hydrogen, nitrogen, formed a very hot atmosphere. During the hot region of this atmosphere, there was certainly interesting chemistry going on. The atmosphere was reasonably oxidative, presumably at that time. But eventually, as it cooled, oceans formed, CO2 was scrubbed, the oxygen content of the atmosphere dropped, and one had a reducing atmosphere, optically thin, whatever that means, at least to the upper regions of the atmosphere, such that photochemistry can occur that built molecules rather than just simply tore them apart. So, what drives this building up of an organic chemistry from methane, N2, or ammonia, or CO? Is it kinetics? Is it thermodynamics? Is it statistics? Unfortunately, it's a combination of all three. As a chemist, I'd like to think that statistics don't play as large a role, that if I simply understand thermodynamics and the rates of all my reactions, then I am going to be able to figure out how this system is going to evolve. Our studies on Titan suggest that statistics, as soon as you're deep in the vacuum ultraviolet, statistics play a critical role. So how can we best seek answers to these problems? How do you go from C1 type systems up to biological or pre-biological molecules that contain nitrogen functionality? How can we understand that? We could try extrapolating back to early Earth, although my close colleague, Jonathan Cunin, used to always remind me that unfortunately on Earth, there's not a carbon atom that hasn't been through a living system. So there's no virgin carbon on Earth, so it's maybe not the best laboratory to try to extrapolate back from. We could look forward to future missions or future optical studies of other objects in our solar system, or I think very importantly, look forward to more examples as we get greater information on exoplanet systems. But what I'd like to do today is just talk mainly about Titan. Until we get sample return, then we're either stuck with the reasonably simple chemical instruments that we can afford to send up in these long missions, or else we can use sophisticated instruments in our laboratory and do our best, or pretend, that we're simulating the environments of these systems. So we spent many years in the first half of my career making interstellar gas clouds in the laboratory at very low temperatures and studying their ion molecule chemistry. More recently, what we've been doing is simulating Titan's ionosphere in the laboratory with the synchrotron and trying to build up a steady state atmosphere of hazy organics. So there's actually two Earth slides. Here's the other one. Hopefully everybody is familiar with the Miller-Urey experiment. And this was back in 1953 was the first paper. And this was an attempt to simulate the conditions of early Earth. We have water, we have hydrogen cyanide, ammonia, carbon monoxide, I forget exactly everything that was thrown into this mixture. And it was cycled, refluxed through a cyclic system where we could put energy in with an electrical discharge. And then after it cooks for a while, under presumably early Earth conditions, go into this ocean and fish out what's been synthesized. And no longer surprisingly, we see the natural amino acids, we see a variety of prebiotic molecules that we think are important. I include this other slide from their paper that shows the energy distributions. They used electrical discharge as the energy distributions on Earth. We're going to study Titan, which is at 10 astronomical units away from the sun, so 100 times lower in energy, but still 95+% of the energy is coming from the vacuum ultraviolet, and so that's what we'll try to focus upon. Okay, Saturn's moon, Titan, as a model, basically it has a rich, nitrogen-rich, 98% nitrogen, a couple percent methane, 50 parts per million, carbon monoxide, a reducing atmosphere. The nitrogen comes from ammonia, photochemistry. It's dry, it's cold, 90-degree Kelvin surface, 170 Kelvin stratosphere, so it's not too bad. Dense atmosphere. And actually underneath the mantle, there is an ocean of presumably ammonia water eutectic. So there's a lot going on Titan. The Cassini mission is extremely successful. Pre-Cassini, there's our understanding of Titan right there, big fuzzy orange ball. It looks like Pasadena in the 60s. Basically, it has a dense organic smog layer. You can't see the surface. Now we can see through the surface at certain wavelengths, infrared wavelengths. There's a rich topography. There's lakes. There's mountains. More importantly, the atmosphere here shows structured layers of haze particles. And we'd like to try to understand that to, again, try and understand what's on this surface and whether it's evolving on Titan or how we can use it to try and understand other objects. Unfortunately, the Huygens probe came back with less information than we would have liked, but still some pretty valuable stuff. The Cassini orbiter was incredible in successes. One of the very first results from Cassini was its mass spectral measurements of the ionosphere. It can't go below about 1,200 kilometers for fear of burning up, but it sampled the ionosphere for many years. But this is the very first mass spectrum that was published. Both ion spectra and neutral spectra. This is a neutral spectrum, and it shows rich organics up in the region of the ionosphere, where on Earth you have N+, O+, NO+, a few nitrogen atoms, maybe a few N2s. There's benzene up there. What that tells you is benzene's rapidly being destroyed by the vacuum ultraviolet at these altitudes, and so there must be mechanisms that are equally rapidly building it back up. perhaps even more surprising, but much less understood, are measurements from another instrument farther out that show positive ions up to mass 300, 350 here, but even more surprising, anions up in the highest regions of the ionosphere up to 10,000 AMU. So there's very, very complex chemistry. We don't know what these are. And presumably, based on what we know about lower in the atmosphere, they're organic based, but that's still an unanswered question. So let me just look at, show you what we think is going on in Titan's atmosphere. You've got the ionosphere up here. Methane, nitrogen is all we really need to focus on initially. We've got very hard vacuum ultraviolet, below 100 nanometers, breaking up nitrogen, ionizing nitrogen, breaking up nitrogen. As we go deeper, we can then finally, we have radiation that's penetrating down deep enough, and it's producing methane in the lower portions. Of course, it's producing methane all through here. Further down, we're producing methyl radicals, and these are combining to make simple hydrocarbons, but they're also combining to make simple nitrogenous organics. Eventually, at these temperatures, these are they're both reacting with each other, but they're also condensing, coagulating to make complex molecules and eventually haze condensates. And this is the orange color down here of Titan. And then these condensates rain down and form an Earth on the surface, presumed to be a couple meters thick, if you talk to the people that are experts on that, of organics, and on a slightly warmer system, or maybe a system with surface water, then these could undergo a richer development. So what can we do in the laboratory to try and understand this? The instruments that Cassini put up there have their limits. They gave us great insight, but can we use more precise measurements on the surface to try and simulate some of these environments and gain some insight as to what this organic sedimentation really is? So we have all the normal tools of the chemist. What we will do is basically do what was highly successful for early Earth, and that is redo the Miller-Urey experiment, but we'll do it in a modern way instead. So here is our reactor that we take to the advanced light source. It's basically simply a photocell. A photocell connected up to an ion mass spectrometer, a neutral mass spectrometer, an aerosol collector, all the things that you need to try and pull the products of this photochemistry out. We put a Titan atmosphere in here at as low a pressure as we can, such that photons are still absorbed in our photocell, run it for a while, and either analyze the mass spectra or collect the aerosols and do more careful analysis. If we collect the aerosols, we can do laser desorption mass spectrometry and start looking at the type of molecules that you have, or at least the type of masses that you get. The very first thing we saw here with a simple mass spectrometer looking actively at the photocell is a spectrum not unlike Cassini's ionospheric spectrum, very rich set of hydrocarbons, better signal to noise so that we can go out and we see higher and higher aromatic ring systems. There's nitrogen in here. I've only pointed out the purely hydrocarbon systems. The peaks to the right of the hydrocarbon systems are not deuterated molecules or nitrogenated molecules, where you've replaced carbons with nitrogen, and you get slightly higher masses. But unfortunately, these assignments are basically predictions based on chemical intuition. What we'd like is absolute determination of molecules, and we're going to need more material than we get from the synchrotron. There's a 200 nanometer thick layer of tholin material, or what Carl Sagan called tholins, after a 16-hour run. So again, you don't get a lot of material. But if you do it in the old-fashioned way, the Miller-Urey way, you take basically a neon sign and a neon sign generator, and you put a Titan mixture through it, turn the sign on, it glows pink, and you come back 24 hours later, and you've got brown powder in there in the milligram, hundreds of milligram quantities, and now you can do some real chemistry. You can look at the morphology of the particles. I don't find, as a chemist, I don't find that all that interesting. These nice round ones were made at Latmos in Paris in a system that levitated their tholins as they were produced and make it nice spherical objects. What we want to do is take our expensive mass spectrometer at Arizona, take these materials, either the thin layer or the bulk solids, ionize them, and mass resolve the products that you get. And there's a typical mass spectrum of this tholin material. Ranges, the cutoff of these ICRs is around 100 or 200. So this is dying off, not because there aren't small molecules there, but just because the throughput of the instrument isn't so good there. But you see masses out to 600, 800, depending on the conditions. Thousands of compounds. You blow that up because you can, and you've got 7 orders of magnitude of precision. And so we can take each one of these peaks and blow it up. This is a 1/10 of an AMU, and you can see you've got 5, 10 different compounds in there. You get the exact molecular formula for every compound. And so from this experiment, we get 5,000 molecular formulae for what's being produced under these conditions, but that still doesn't give you structure. And that's really what we want. We want to give structure so we can understand, we can talk to the biochemists as to what we really have there. If you take those 5,000 peaks and do what the petrochemists did in the 50s and 60s, and plot nitrogen to carbon ratio versus hydrogen to carbon ratio for every one of those, and put them as a point on this slide, you get what they call a Van Crevelen diagram, and it provides you some insight as to the origins of these large molecules. Peaks up in here presumably come from hydrogen cyanide type chain reactions. This is an important point here. This comes from HC2N radical. PAHs would be down here. And so you can look at these, especially with the synchrotron, as a function of radiation wavelength. If you look at 82.5 nanometers, where you produce mainly nitrogen quartet S, nitrogen doublet D atoms from the nitrogen, and you're cracking methane as well and ionizing methane, you see a mixture that looks like it derives from hydrogen cyanide, 1-to-1 on the Van Crevelen diagram. If you tune deeper to 60 nanometers, then you start seeing a mixture that was produced from a different set of intermediates. We simply built a trivial model. We're experimentalists, but we can still try and model once in a while. And we built a model with about 20 to 30 starting materials, rates for coagulation, rates for chemical reactions between them, turned it on and ran it for a while, and we can simulate these based on the known photochemistry of methane and N2 at these wavelengths. So it is predictable as complex as these mixtures are. And just to remind you, this stuff is incredibly rich in nitrogen, which again leads to its chemical potential, tremendous chemical potential. And so from these sorts of studies, we still don't know the structures of the large molecules, but from our models, we can build reaction pathways that explain the first steps to the hard photochemistry that's occurring, and get some insights into this. I want to finish up. We stick this stuff in water, as Miller and Urey did. Then, of course, we get amino acids. This stuff has all the potential. If we add a little bit more carbon monoxide into the plasma, then we get nucleobases. And so this stuff has all the potential for making astrobiological molecules. But what we'd like to do is figure out what's really there. And so nuclear magnetic resonance comes to the rescue. The beauty of laboratory experiment is we can go in and we can now make these tholins using 100% C13 labeled methane, 100% N15 labeled nitrogen, normal hydrogen, and make tholins where every atom in the tholin is a spin 1/2 nucleus, and then put them in a magnetic field, split those nuclear spin states, which all talk to each other, and they talk to their nearest neighbors, and we can take a mixture of 5,000 compounds and pick out a single molecule in the NMR and walk down its chain and figure out which atoms are connected to which, go to another peak, which is another molecule, and do exactly the same thing. And if I had 50 postdocs in 20 years, we probably could identify all of the molecules. So we can use all of these standard multi-dimensional NMR techniques, just one-dimensional, tickle hydrogen and see what frequency it emits at, tickle hydrogen and see what other hydrogens it excites, tickle hydrogen, watch it excite nitrogen, which then excites carbon and comes back to hydrogen and gives you a signal. And we can slowly pick apart these spectra and get the correlations between the peaks in the unresolved spectrum and figure out which molecules are at least most prominent in this mixture. And here is just the sampling of our most recent set of molecules, high amounts of nitrogen. Again, I'm not a biochemist. I'm a small molecule physical chemist. And so I just show these structures here for the fact that we can pull them all out. And so some of them are fragments of structures, and slowly figure out what's being produced. The bottom line is there is a very rich chemistry on Titan with a high prebiotic potential. And this is just, we see HMT, and we see the precursors to HMT. HMT is also seen in interstellar gas clouds via similar mechanisms. So HMT seems to be a ubiquitous molecule in the universe, not very reactive. The nitrogen is tertiary, but some commonality with interstellar type reactions. So the take-home lessons are we think atmospheres are important. Nitrogen is critical in producing the reducing atmosphere, but also giving a richness to the functionality that's produced. And laboratory work certainly has its place in helping modelers and mission scientists figure out what's going on in our complicated world. I want to spend my last 20 seconds, I guess, saying a couple things about chirality. Kenzo did a great job of it, talking about shaking hands. Hands are mirror images of each other. if you shake right to right, it's a diastereomeric interaction. If I grab an acetone molecule with my right hand and an acetone molecule with my left hand, acetone is not chiral. The thermodynamics of that interaction are exactly the same, 100%. And so they should react the same. If I grab a left-handed sugar with my right hand and a left-handed sugar with my other hand, the diastereomeric pair has its own unique thermodynamics. This leads to different melting points in diastereomeric molecules and what have you. So it's these interactions. Why did nature choose a homochiral pathway to use in life, whether the homochiral pathways were produced before life or chosen after the beginnings of life? It was expensive to do that. Basically threw away half of the molecules that were present there on your palette in order to only react with the left-handed molecules or the right-handed molecules. And I have a mental block as to which are which when it comes to sugars and amino acids. I'll just point out that in the absence of a diastereomeric interaction, chiral, then the thermodynamics and the barriers for chemical reactions and the kinetics all have to be the same. However, if you've got a chiral reagent reacting to form a new chiral center, then the barriers for the reaction differ, and one can have an enantiomeric selection. And that's pretty much all I want to say about that. There's a nice example. These bugs are in Tucson as well as in England. Here is a case where this bug's shell is chiral, and it reflects left circularly polarized light, but the right circularly polarized light gets used as energy. So again, I will just pretty much, I'm out of time, and so I will end with this. Why did Earth choose a homochiral path? Why didn't it use all the sugars available to us? And I think it has to do with information content. The interactions of single enantiomers to produce diastereomeric pairs dramatically increases the information content when you've got multiple chiral centers. And this is effectively a form of chemical communication that allowed tertiary structure to be as selective, enzymes to be as selective as they are. How it emerged, I have no idea. Happy to talk about it, but it's one of the vexing problems in organic chemistry. And then finally, I just want to thank my collaborators over the last 15 years of this type work. And thank you for listening.
Well, great. Thank you very much. Ready to take some questions?
Oh, nice.
Thank you for the talk. That was great. So it was actually more of a maybe technical question about your tholins. So does those systems create any larger molecules that might not fly them a speck or might not dissolve for your solution in NMR or don't tumble? And would you estimate how much of what fraction of those is there, and how would you go about analyzing those?
Yeah, the answer is yes. It really depends on how much energy you put in per mole of atmosphere. You can make material that's 100% refractory, dissolves in nothing. But if you do it more carefully, then you get these nice, simpler mixtures of molecules. So yeah, you have to worry about that. And so this, I think, can help teach us what could happen on Titan. This is not Titan tholin. This is laboratory tholin.
Oh, of course.
Yeah, no, but that's an important point. We're not making Titan material. We're simulating Titan's environment to try and understand the type of things that can happen.
Thank you.
Thanks. I guess my question is similar to this latest question on Slido, is Titan alive? So what do we know about Titan's geological activity? And I mean, that seems pretty important for... That seems pretty important for Earth, obviously. You get a cycling of materials into pretty different environments between the surface and subsurface.
Yeah, I'm not the person to ask about that. I don't know of active mixing between the surface and the subsurface. The nitrogen would have long ago gone away because of photochemistry, and the hydrogen, well, the losses out of the atmosphere because Titan's a little smaller, the gravitational field's weaker. And so there is a continual source of replenishment of both the methane and the nitrogen. How deep that involves the mantle is, I don't think, quite well understood. The oceans underneath the mantle are based on density measurements of the planet as a whole. There's no obvious signs of a water upwelling. There's lakes on Titan, but they're hydrocarbons. They're from production in the atmosphere. So I think there are other people that really you should talk about their plate tectonics on Titan.
I just mean that seems like it could be a big difference between early Earth and
yeah,
Titan.
Sure. No, and when I say it's the closest thing we have to early Earth, I'm speaking as a chemist, an organic chemist. Geologically, I'd love to talk to you about it.
Yeah, to address your question, the Titan surface is really young, based on the crater chronology. So it's 2 billion years, less than 2 billion years. So some replenishment process would have occurred on Titan. And I have another question. From a view of comparative planetary chemistry, Pluto's organic chemistry and organic aerosol is another very important topic.
Sure.
Because the Pluto's atmosphere contains CO as a source of oxygen atom in the atmosphere. So did you do the experiment by adding the CO in the system? And if so, how and in what form the oxygen atom would be incorporated into the higher molecular weights molecule?
We've done studies as a function of CO, and you get similar complex mixtures. We haven't studied them in depth with NMR, for instance, to sort out all the compounds. I know that Hiroshi Yamanaka, who worked with me for a long time, is now trying to do this.
Yeah.
You see tholins on Pluto's surface, and so there are people actively doing this. We're not.
Okay, thank you.
You mentioned your 3 a.m. epiphany about emergence and all this. I wonder if you could share that just a little bit with us?
It just seems to me that there is no strong driver for Earth to have chosen homochiral pathway. I mean, there's certainly benefits to choosing a homochiral pathway in terms of information content if you're going to then start making RNA and DNA and enzymes that have precise structures that you want. But there's no firm driver. There's some theories on this. The nuclear weak effect supposedly splits the energy levels of enantiomers, but I forget 10 to the -5 wave numbers or something like this. So I mean, it's not a strong effect that easily translates into enantiomeric excess. It seems to me that the emergence of homochirality fits some of the definition of emergence in the sense that it's surprising, it's not explainable based on principles that we know. Any principles regarding catalysis by clays or catalysis by quartz crystals will average to 0 across the Earth. And so in my mind, there's no reason that globally, Earth would have gone down a single pathway. And so, I'd love to stimulate some discussion to try and see what other people's who have also thought about this problem think about its origins. We know its consequences. Yeah.
So somebody's your yes notes in the past. First one was, has an NMR with a Saturn space?
No, we're trying to do that. At JPL, we worked on getting a little 40 megahertz NMR, and we simulated what the NMR of a lake would look like, because the idea is send a balloon around and sip some lake fluid and analyze it. We'd like to send it into a small NMR. But as soon as I mentioned that it would also need carbon capability, the interest went away. The power requirements for the RF and everything just get a little high.
It
needs to be done, though.
Yeah. Is there any evidence for lightning or plasma discharges in Titan's atmosphere?
Yes, there are, but it's controversial. I think there are events that suggest lightning. On Titan, there are clouds, but it's not prevalent, and I'm not sure how firm those go back 5 or 6, 7 years, and I haven't followed that.
If we can launch the microphone back there, or okay.
Thank you. So I'm curious about since you're talking about atmospheric chemistry, can you imagine a mechanism by which life on a planet could actually not be homochiral? Because to me, that seems more difficult if you have things that are replicating and competing with each other.
As a small molecule chemist, I don't see why homochirality. Well, yes, homochirality. The molecules would need to be much more complicated. I mean, I think that the homochirality allows a modest-sized molecule to contain information content for binding specific molecules, doing specific reactions, catalytic reactions, that are more difficult if you just have racemic mixtures everywhere.
Well, I guess
there's no reason. The bottom line is everything could be racemic and follow pathways along certain molecules, but then what's going to make the other isomers, and why would they be made?
So the question, I guess, is that if you have something which is autocatalytic, then the inputs to that, if they're chiral, like if you have molecules that are chiral but maybe racemic in a mixture, that autocatalytic process amplifies any fluctuations. So without any kind of homeostatic mechanism, you will go to a pure mixture one way or another just in the presence of replication. So there would have to be some mechanism to actually push you back towards a racemic mixture for that to be stable over 4 billion years.
Yeah, well, that's related to my question to Kenzo is, but then over in another state or county or city, the opposite would be happening, and over the globe, it would just average to zero. I mean, because the autocatalytic reaction, unless the autocatalytic reaction involved specific diastereomeric pairs, and then you can get different thermodynamics that can lead to energetic selectivity.
I don't want to turn this into a. Yeah, we can discuss it after.
Please do.
Well, let's consider about organic compound. The simple organic compound, that is a saturated hydrocarbon, non-acyclic. That means CnH2n plus 2, methane, ethane, propane, butane. They are not chiral, of course, but when the number of carbon atom becomes, let's say 10 or 14, that's the tetradecane, there are a tremendous number of isomers, and 95% of isomers are chiral. That means the chirality is the natural phenomenon. The problem is the very interesting thing of life is that is the enriched chirality is very characteristic feature. So chirality is not the rare phenomenon.
So yeah, what you're saying is there are tons, the bulk of organic matter on Earth is racemic. And yet the molecules that biology is using is just selecting out a few and only using one enantiomer. So, yeah.
Thank you so much. I think we need to stop. We're a little bit over time, so let's thank the speakers again.